Hello everyone. So we already have started discussion associated with sensor physics. We have seen physics associated with different types of sensors. For example, say capacitive sensor. So in today's lecture, we will try to see some numerical problems associated with say capacitive sensors. While we are discussing these problems, we'll also check or discuss certain physics associated with sensors as well, so that you can connect with the problem as far as the sensing aspect is concerned. Some of the sensor physics or most of the sensor physics associated with these problems are already discussed. I think it's very clear now to all of you, but still I may repeat some of these considerations so that the discussion remains well connected with the sensor physics that we already have discussed. And the problems are taken from different sources. One may see similar problems in previous GATE papers or any competitive exam papers as well. So let us start with a very basic problem and an interesting problem associated with capacitive sensor. So the question here is, the distance between the extreme plates of a differential capacitive sensor is 100 mm as shown in the figure. So this is the figure where the distance between the extreme plates, that is plate 1 and plate 2, the distance between these two plates are 100 millimeter. Now the difference voltage, that is delta V, equal to V1 minus V2, where V1 and V2 are the RMS values. So this is say the value of V1, this is the value of V2. So the difference voltage for a downward displacement of 10 mm of the intermediate plate from the central position is, we need to figure that out. So what they are saying is, this is your sensor structure where you have two plates 1 and 2, they are separated by a distance of 100 mm, and it also has an intermediate plate, say plate 3. Now if this plate deflects by 10 mm in the downward direction, then what will be the difference voltage? If it is in the middle, say the voltage is V1 and V2. Now if it goes down by 10 mm, then what will be the V1 minus V2 value, that is delta V value. Now the structure here is similar to, or you can correlate this structure with a say MEMS sensor. So you have a MEMS sensor, you have designed a sensor where this is the upper plate, this is the lower plate, and then you have an intermediate plate over here which is movable. Okay, if the entire system is in acceleration towards upward direction, you may find that this plate, the intermediate plate, moves down or moves in the downward direction. Now if the acceleration is higher, maybe this plate will move further down. From that one can understand what is the acceleration value. Okay, because this plate will be in the inertia, the moment you start moving that plate or moving the entire system, this plate will come down because it's movable. So that is a kind of sensor consideration that you may consider, which is related to this problem. Okay, now if you can figure out the differential voltage for this 10 mm displacement, then from that particular voltage you can also calibrate the entire sensor system. I mean, it's not a single measurement, you need to take multiple measurements. In fact, you can derive an equation also how this distance d is related to delta V, and that equation will help you to figure out the calibration curve of this sensor, calibration curve with respect to distance for this particular sensing system. But let us first solve this problem that is given to us. Now, the voltage applied across this sensing arrangement is 10 volt as it is shown over here, right. So, let us consider that the deflection of this intermediate plate is x. Now, say the new position of the intermediate plate is here. So, in such a situation, the capacitance C1, that is the capacitance between first plate and the intermediate plate, is equal to epsilon A divided by d plus x, because the distance now is d plus this distance x, right. So, the C1 is equal to epsilon A divided by d plus x. Similarly, the value of C2 will be d minus this value, because now this plate is in the new position. So, for C2 the value is epsilon A d minus x. So, in the first case C1 is epsilon A divided by d plus x. In the second case C2 is epsilon A d minus x. So, we know C is equal to epsilon A by d, where d is the distance. So, according to the new distance, the distance associated with C1 is now d plus x. However, the distance associated with C2 now is d minus this x, because the plate has now moved in the downward direction. So, similarly you can say that the value V1, that is voltage associated with C1, is equal to C2 divided by C1 plus C2 into V, right, because you can consider the entire arrangement as C1 and then C2, which is connected to V, right. So, in this arrangement the voltage across C1 is equal to C2 divided by C1 plus C2 into V, and V2, that is voltage across C2, is C1 divided by C1 plus C2 into V. This is something associated with simple circuit analysis. So, V1 is equal to, put the values of C2 and C1 in this equation, epsilon A divided by d minus x divided by epsilon A divided by d plus x plus epsilon A divided by d minus x into V. If you rearrange this part of this equation, you will find your V1 is d plus x divided by 2d into V. Similarly, if you do the same analysis for V2, and if you rearrange this equation, you will find your V2 is equal to d minus x divided by 2d into V. So, your V1 minus V2 is this minus this. If you do this, you will find that the answer is d plus x divided by 2d into V minus d minus x divided by 2d into V. So, this is your V1, this is your V2. Take V in common from both the term, and then if you do the arrangement, or if you do that subtraction, you will find this value is nothing but x by d into V. Now, you know the value of x, 10 mm, because in the problem itself it is written that the plate has moved down by 10 mm, and the value of d is 50 mm. Why? Because you have considered the initial distance between intermediate plate and the first plate as d, and the initial distance between the intermediate plate and the second plate is another d. So, your 2d is equal to 100 mm. So, your d is equal to 100 by 2, that is 50. So, 10 mm by 50 mm into 10. So, if you do the simple maths, you will find your V1 minus V2, that is delta V, is equal to 2 volt. So, that is how you can calculate the differential voltage in this situation. So, this is how you can solve a particular problem, right. Similarly, you can take another problem where A capacitive transducer consists of two parallel plates as shown over here, and the diameter of the plate is 2 cm, and the gap between these two plates is 0.25 mm as it is shown over here. Now, assuming a linear response, the displacement sensitivity of the sensor is. So, you have to figure out what is the displacement sensitivity. That means the sensitivity of the entire sensor with respect to the displacement. That is what we need to figure out. So, in this case, you can compare this with a system where you have a bottom plate and a top plate, but the top plate is say movable. Okay, there is some spring arrangement, so the top plate is movable. Now, what you have to figure out that what is the sensitivity with respect to displacement. That is, if this the first plate is movable, then it will move up and down. So, what is the sensitivity associated with displacement? So, in this case, the displacement sensitivity of the transducer can be given by dc dx, because if you have an equation between c and x, there must be some equation between c and x whatever polynomial it is. So, the slope associated with this will give you the displacement sensitivity. We know the slope corresponds to the sensitivity. So, your displacement sensitivity is the response, the different derivative dc dx, where x is the displacement. So, you have to do the derivative with respect to displacement. Now, capacitance is nothing but C is equal to epsilon 0 A by x. That means dc dx in this case is minus epsilon 0 A divided by x square. If you do the derivative of 1 by x, it is nothing but minus 1 by x square, right? Where A in this case is the area of the plates and x is the distance between the plates. This is x and the area is A. This is the area. So, because both the plates are circular in nature, the area can be calculated with this equation. A is equal to pi r square, where the value of r, so this is the value of d, right? So, this is the value of d. So, your r is your r is equal to d by 2, that means 2 by 2 centimeter, that is 1 centimeter. So, 1 centimeter is nothing but 1 into 10 to the power minus 2 meter. So, it is pi into 1 into 10 to the power minus 2 whole square. So, this will give you pi into 10 to the power minus 4 meter square, right. Now, distance between the plates x is equal to 0.25 mm, that is what we know. So, your displacement sensitivity HD is equal to dc dx is equal to minus epsilon 0 A by x square. The value of epsilon 0 is given over here. The value of A we have just calculated, pi into 10 to the power minus 4, and the value of x is 0.25 mm. At this point only the sensitivity we need to calculate. So, just put the value of 0.25 mm in here. It is x square. So, 0.25 square into 10 to the power minus 3 whole square, that is 10 to the power minus 6. Do this calculation, the answer will be minus 444 into 10 to the power minus 10 farad per meter. You can also calculate the value with farad per centimeter unit. Maybe in that case the value will be 444 picofarad per centimeter. You do this calculation, you will be able to just convert meter into centimeter, then you will be able to figure it out. So, this is the displacement sensitivity at x equal to 0.25 mm, right. Now, the negative sign indicates that the response decreases with respect to stimuli. So, if you increase the stimuli, then the sensitivity, that is the slope, is negative, right. So, that is what it means. So, this is another problem associated with capacitive sensor. Now, let us see another problem where it says a capacitive transducer uses 2 quartz diaphragm of area 750 mm square separated by a distance of 3.5 mm. The capacitance is 370 picofarad. When a pressure of 900 kilonewton meter square is applied, the deflection is 0.6 mm. Assuming homogeneous deflection between plates, the capacitance at this pressure is what? So, what they are saying is there is a capacitive transducer that uses two quartz diaphragms. So, this is one diaphragm, this is another diaphragm. Let us say this is diaphragm 1, this is diaphragm 2, and the area associated with this diaphragm is 750 mm. So, here also the area should be 750 mm square, and these two diaphragms are separated by a distance of 3.5 mm. The capacitance at this stage is 370 picofarad. So, when the area is 750 mm square, when the separation here is 3.5 mm, the capacitance value is 370 picofarad. Now, when 900 kilonewton per meter square pressure is applied, say in one diaphragm, then the deflection is 0.6 mm. So, it comes down by say 0.6 mm. Now, if you assume a homogeneous deflection between the plates, that means when you apply the pressure, the entire diaphragm will come close to the bottom diaphragm. The entire top diaphragm will come close to the bottom diaphragm. So, this deflection is homogeneous across the plate. The capacitance value we need to now measure at this condition when the pressure is this and deflection is this. Okay. Now, we know capacitance C is equal to epsilon A by D. In this case, your A is constant, but the distance between the plates, that is D, is not constant. So, your D changes. Now, we know C is proportional to 1 by D. From this equation only, it is very much evident. If distance increases, capacitance will decrease. If distance decreases, capacitance will increase. Now, consider at this situation, the capacitance is C1. After you apply the pressure, the capacitance is C2. Now, the ratio C1 by C2 will be equal to D2 by D1 because it is inversely proportionate. So, you can consider, say, from here also you can write C1 is equal to epsilon A by D1, C2 is equal to epsilon A by D2. So, D1 is the distance when capacitance is C1, D2 is the distance when capacitance is C2. Now, if you do C1 by C2, then it will be equal to epsilon A by D1, epsilon A by D2, epsilon and epsilon A will get cancelled. So, it will ultimately be D1 divided by D2. So, your C1 by C2 is equal to D2 by D1, right. Now, in this case, our C1 is 370 picofarad and D1 is equal to 3.5 mm when P is equal to 0. In second case, your D2 is D1 minus D, because now once you apply the pressure, this plate will come down by 0.6 mm. That is what is said over the problem statement. So, your D2 is equal to D1 minus D, that is 3.5 minus 0.6. So, it is like 2.9 mm, which is equal to 2.9 into 10 to the power minus 3 meter. The deflection D is 0.6 mm, which is equal to 6 into 10 to the power minus 4. Area A is equal to 750 mm square, which is 7.5 into 10 to the power minus 4 mm square. Sorry, it is m square, meter square, if you convert it to meter square. Your D is equal to 3.5 mm, that is 3.5 into 10 to the power minus 3 m meter, which is D1 in this case. Your capacitance C is 370 picofarad, that is 3.7 into 10 to the power minus 10 farad, which is C1 in this case, and applied pressure P is 900 kilonewton per meter square, that is 9 into 10 to the power 5 Newton per meter square. Now, put these values in here. So, your C2 is equal to C1 into D1 by D2. So, it is D1 by D2 into C1. Now put the values. D1 is 3.5 into 10 to the power minus 3 meter. D2 is 2.9 into 10 to the power minus 3 meter. Your C1 is 370 picofarad. So if you do this calculation, you'll figure out that C2 is 446.5 picofarad. So the value of the capacitance when you apply a pressure of 900 kilonewton per meter square will be 446.5 picofarad. So that is how you can calculate the capacitance value associated with this sensor. So these are few problems that I have solved. There are similar problems you may encounter even during the sensor design or when you are designing different capacitive sensors. So in those cases, these approaches will help you in designing and solving problems associated with sensor structure. In the upcoming discussion, we will discuss more about different sensor physics. Till then, thank you.